What if I told you that somewhere in the vast expanse of space, there exists a place where time itself bends and breaks, where the laws of physics as we know them cease to make sense? Black holes, those enigmatic cosmic giants, are not just voids in space, they are the ultimate mystery, capable of warping reality in ways that challenge our understanding of the universe. Today, we're diving into the unknown, uncovering 20 mind-blowing facts about black holes that will leave you questioning everything you thought you knew. From their ability to spin at nearly the speed of light to the eerie possibility that they might even sing, these cosmic phenomena hold secrets that are as fascinating as they are terrifying. So buckle up and prepare to explore the depths of these celestial wonders, because by the end of this video, you'll see the universe in a whole new light. Let's begin our journey into the heart of the unknown. Now, let's clear up one of the biggest misconceptions about black holes. Despite their name, black holes aren't actually holes at all. They're not empty voids or cosmic vacuums sucking everything in. Instead, they are incredibly dense objects with a gravitational pull so strong that nothing, not even light, can escape once it crosses a certain point known as the event horizon. The name black hole can be misleading because it conjures up images of an empty space, but in reality, these objects are packed with matter. Imagine taking a star several times more massive than our Sun and squeezing it down into a tiny, unimaginably dense point. That's what we call a singularity, a place where matter is compressed into an infinitely small space, creating a gravitational field so intense that it warps the very fabric of space and time around it. So, while the term black hole might make you think of an empty pit, it's really more like a cosmic heavyweight champion, bending the rules of physics and challenging our understanding of the universe. And this is just the beginning. There's so much more to uncover about these fascinating objects. Now, shifting our focus to another mind-bending aspect of black holes, let's talk about their ability to spin, and not just spin, but spin at nearly the speed of light. Yes, black holes aren't just static objects sitting in space. Many of them are rotating at incredible speeds, and this rotation has profound effects on the space-time around them. Imagine a cosmic whirlpool where the black hole's spin drags everything nearby into a swirling dance. This region around a spinning black hole is called the ergosphere, a zone where space-time itself is twisted and pulled along with the black hole's rotation. Inside the ergosphere, nothing can stand still, not even light. This phenomenon is known as frame dragging, where the black hole's spin literally drags the fabric of space and time around with it. It's like being caught in a cosmic current where the rules of physics as we know them start to bend. The faster the black hole spins, the more extreme these effects become, creating a dynamic and chaotic environment that challenges our understanding of the universe. So, while black holes are already mysterious enough, their ability to spin at such incredible speeds adds another layer of intrigue to these cosmic enigmas. And this is just the tip of the iceberg. There's so much more to explore about how black holes shape the universe around them. Now, as we venture deeper into the mysteries of black holes, let's explore a phenomenon that might surprise you. Black holes can actually sing. Yes, you heard that right. These cosmic giants, often thought of as silent voids, can produce sound waves, but not in the way you might expect. Instead of traditional sound, black holes create ripples in the fabric of space-time known as gravitational waves. These waves are like cosmic vibrations, traveling across the universe and carrying with them the songs of black holes. Scientists have detected these gravitational waves using incredibly sensitive instruments like LIGO, the Laser Interferometer Gravitational Wave Observatory. When two black holes collide or merge, they send out powerful gravitational waves that ripple through space-time. These waves can be translated into sound, revealing the unique chirps or tones of the black holes involved. Each collision produces a distinct pattern, almost like a musical note, giving us a glimpse into the black hole's masses, spins, and even their distances from Earth. What's truly fascinating is that these songs aren't just cosmic curiosities, they're a treasure trove of information. By analyzing the frequencies and patterns of these gravitational waves, scientists can uncover details about the black hole's properties, such as how massive they are, how fast they're spinning, and even how they formed. It's like listening to a cosmic symphony where each note tells a story about the universe's most enigmatic objects. So, while black holes might seem silent and invisible, they're actually broadcasting their presence across the cosmos in ways we're only beginning to understand. And as we continue to listen to these gravitational waves, we're unlocking new secrets about the nature of black holes and the universe itself. But the surprises don't end here. There's still so much more to discover about these incredible phenomena. Now, shifting our gaze to another astonishing aspect of black holes, let's explore a theory that might seem counterintuitive at first. Black holes can actually evaporate. This idea, proposed by the legendary physicist Stephen Hawking, challenges the notion that black holes are eternal. According to Hawking's theory, black holes aren't just cosmic vacuum cleaners that suck in everything forever. Instead, they can slowly lose mass and energy over time through a process called Hawking radiation. Here's how it works. In the quantum world, empty space isn't truly empty. It's filled with pairs of particles and antiparticles that constantly pop into existence and then annihilate each other. Near the edge of a black hole, known as the event horizon, one of these particles can fall into the black hole while the other escapes into space. The escaping particle carries away a tiny bit of the black hole's energy, causing it to lose mass. Over incredibly long periods of time, this process can cause a black hole to shrink and eventually evaporate completely. But don't expect this to happen quickly. For a black hole the size of our Sun, the process would take far longer than the current age of the universe. Smaller black holes, however, could evaporate much faster, releasing bursts of energy as they disappear. This has fascinating implications for the lifespan of black holes and the fate of the universe itself. If black holes can evaporate, it means they're not the eternal prisons we once thought they were. Instead, they're dynamic objects with a beginning, a middle, and an end. Hawking radiation also raises intriguing questions about what happens to the information that falls into a black hole. According to quantum mechanics, information can't be destroyed, but if a black hole evaporates, where does that information go? This puzzle, known as the black hole information paradox, remains one of the biggest unsolved mysteries in physics. So, while black holes might seem like the ultimate cosmic dead ends, Hawking's theory reminds us that even these enigmatic objects are subject to the laws of physics. They're not just static voids, they're evolving, dynamic entities that challenge our understanding of the universe. And as we continue to unravel their secrets, we're reminded that even the darkest corners of space hold surprises waiting to be discovered. Now, shifting our focus to the incredible diversity of black holes, let's explore a surprising fact. Black holes aren't all massive, galaxy-devouring giants. In fact, they can be astonishingly tiny. While we often picture black holes as colossal objects with masses millions or even billions of times greater than our Sun, they can also exist on a much smaller scale. Some black holes could be as small as an atom, yet still pack an unimaginable amount of density and gravitational power. These miniature black holes, often referred to as micro-black holes, are a fascinating theoretical possibility. They're thought to form under extreme conditions, such as during the early moments of the universe. Scientists speculate that in the chaotic environment just after the Big Bang, regions of space with incredibly high density could have collapsed into tiny black holes. These are called primordial black holes, and they could be as small as a single atom but contain the mass of a mountain. Imagine something so small yet so dense that it bends space and time around it just like its larger counterparts. The existence of primordial black holes is still a topic of debate, but if they do exist, they could help us answer some of the biggest questions in physics. For instance, they might even explain the mysterious dark matter that makes up a significant portion of the universe. Because they're so small and difficult to detect, primordial black holes could be hiding in plain sight, scattered throughout the cosmos, influencing the universe in ways we're only beginning to understand. What's truly mind-boggling is how these tiny black holes behave. Despite their size, they would still have an event horizon, the point of no return where gravity becomes so strong that not even light can escape. And just like larger black holes, they could evaporate over time through Hawking radiation, though the process would happen much faster due to their smaller size. In fact, a micro black hole might only last for a fraction of a second before vanishing in a burst of energy. This incredible range in size, from the tiniest micro black holes to the supermassive behemoths at the centers of galaxies, shows just how versatile and mysterious these cosmic objects are. Whether they are as small as an atom or as large as a solar system, black holes continue to challenge our understanding of the universe and remind us that even the smallest things can have the biggest impact. And as we continue to search for these elusive micro-black holes, we're reminded that the cosmos is full of surprises waiting to be uncovered. Now, turning to one of the most mind-bending ideas in modern cosmology, let's explore the possibility that black holes might not just be cosmic destroyers, they could also be cosmic creators. Imagine this: what if every black hole is a gateway to an entirely new universe? This speculative theory suggests that inside the heart of a black hole, beyond the singularity, lies the potential for an entirely new cosmos to form. It's a concept that sounds like science fiction, but it's rooted in some of the most cutting-edge ideas in physics. This idea ties into the concept of the multiverse, the idea that our universe is just one of countless others, each with its own unique set of physical laws and constants. According to some theories, when matter collapses into a black hole, the extreme conditions at the singularity could trigger the birth of a new universe. In this scenario, the black hole's singularity acts like a cosmic seed, sprouting a new reality that expands outward, completely separate from our own. It's as if every black hole is a doorway to another dimension, hidden within the fabric of space-time. But how could this even be possible? To understand this, we need to dive into the strange world of quantum physics. At the quantum level, particles can pop in and out of existence, and space-time itself can behave in unpredictable ways. Some physicists suggest that the singularity inside a black hole might not be a point of infinite density, as classical physics suggests, but rather a kind of quantum bridge to another universe. This bridge could allow the energy and information that falls into the black hole to be reborn in a new cosmic realm, effectively creating a new universe. This theory also raises fascinating questions about the nature of reality itself. If black holes can create new universes, does that mean our own universe could have been born from a black hole in another cosmos? It's a thought that challenges our understanding of beginnings and endings, suggesting that the universe might be part of an endless cycle of creation and destruction. Of course, this idea is still highly speculative, and there's no direct evidence to prove it yet, but it's a testament to the power of black holes to inspire both awe and curiosity. They're not just mysterious objects, they're windows into the deepest questions about existence, reality, and the very fabric of the cosmos. And as we continue to study these enigmatic phenomena, we might just uncover clues that reveal whether black holes are truly the architects of new universes. Now, shifting our focus to one of the most dramatic effects of black holes, let's dive into the bizarre and terrifying phenomenon known as spaghettification. Imagine this: you're floating in space, minding your own business, when suddenly you find yourself drifting toward a black hole. As you get closer, the immense gravitational pull begins to stretch you literally. This is spaghettification, a process where the gravity of a black hole is so strong that it pulls harder on the side of your body closest to it than on the side farther away. The result: you're stretched into a long, thin shape like a piece of spaghetti, Here's how it works. As you approach the black hole, the difference in gravitational force between your head and your feet becomes extreme. If your feet are closer to the black hole, they're pulled much more strongly than your head. This tidal force stretches you lengthwise while simultaneously compressing you sideways. It's like being pulled apart and squeezed at the same time. The closer you get to the black hole, the more intense this effect becomes until you're stretched into an impossibly thin strand. But it's not just your body that's affected. Every object, no matter how strong, would undergo the same process. A spaceship, a planet, even a star, nothing can withstand the relentless pull of a black hole's gravity. The process is so extreme that it's hard to even imagine. Picture a rubber band being stretched to its absolute limit, but instead of snapping, it just keeps stretching thinner and thinner until it's almost invisible. What's even more fascinating is that this isn't just a theoretical idea. Scientists have observed the effects of spaghettification on stars that get too close to black holes. These stars are torn apart in a process called a tidal disruption event, where the black hole's gravity rips the star into streams of gas, stretching it into long, thin filaments before swallowing it whole. It's a cosmic spectacle that highlights just how powerful and destructive black holes can be. So, what would it feel like to experience spaghettification? Well, it's not something anyone would survive, but if you could, the sensation would be unlike anything imaginable. You'd feel an intense stretching force, as if every atom in your body were being pulled apart. It's a reminder of just how extreme the conditions around a black hole can be, and how much we still have to learn about these mysterious objects. As we continue to explore the strange and fascinating world of black holes, spaghettification stands out as one of the most vivid examples of their power. It's a phenomenon that challenges our understanding of physics and reminds us just how alien the universe can be. And while it's a terrifying thought, it's also a testament to the incredible forces at work in the cosmos. Now, shifting our gaze to one of the most dazzling phenomena in the cosmos, let's explore how black holes, especially the supermassive ones, can power quasars, some of the brightest objects in the universe. Quasars, short for quasi-stellar radio sources, are incredibly luminous and can outshine entire galaxies. But what makes them shine so brightly? The answer lies in the heart of these cosmic powerhouses, supermassive black holes. At the center of every quasar, there's a supermassive black hole, millions or even billions of times more massive than our Sun. But it's not the black hole itself that emits light, it's the material swirling around it. This material forms what's called an accretion disk, a swirling, superheated ring of gas, dust, and debris that spirals inward toward the black hole. As this material gets closer to the event horizon, it heats up to extreme temperatures reaching millions of degrees. This intense heat causes the disk to glow brightly, emitting vast amounts of energy across the electromagnetic spectrum, from radio waves to X-rays. But how does this process generate so much energy? It all comes down to friction and gravity. As particles in the accretion disk collide and rub against each other, they release energy in the form of heat and light. At the same time, the black hole's immense gravitational pull accelerates the material to incredible speeds, further heating it up. This combination of friction and gravitational energy makes the accretion disk one of the most energetic environments in the universe. What's truly mind-blowing is the sheer scale of this energy output. A single quasar can emit thousands of times more energy than an entire galaxy, all from a region no larger than our solar system. This makes quasars some of the most powerful and distant objects we can observe, acting as cosmic lighthouses that help us peer into the early universe. Interestingly, quasars aren't just bright, they're also incredibly active. Some quasars shoot out jets of particles at nearly the speed of light, extending millions of light years into space. These jets are thought to be powered by the black hole's magnetic fields, which channel some of the energy from the accretion disk into narrow, high-speed streams. These jets can influence entire galaxies, shaping their evolution and even triggering the formation of new stars. So, while black holes are often thought of as dark, invisible objects, their ability to power quasars shows just how dynamic and influential they can be. Through the process of accretion, they transform ordinary matter into extraordinary energy, lighting up the universe in ways that continue to astonish us. As we uncover more about these cosmic engines, we gain a deeper understanding of the forces that shape the cosmos and the incredible role black holes play in the grand tapestry of the universe. Now, let's dive into a concept that might sound a bit strange at first: black holes having hair. No, we're not talking about actual hair, but rather a fascinating idea that challenges one of the most fundamental theories about black holes, the no-hair theorem. This theorem, proposed in the 1960s, suggests that black holes are incredibly simple objects defined only by three basic properties: their mass, their electric charge, and their spin. According to this idea, no matter how complex the material that falls into a black hole might be, all other information about it is lost forever, leaving behind a black hole that's essentially bald. But here's where things get interesting. Recent research has begun to challenge this long-standing theorem, suggesting that black holes might not be as simple as we once thought. Scientists have proposed that black holes could have hair, additional properties or subtle features that encode more information about their history and the matter that formed them. This hair isn't something you can see or touch, but rather a way to describe how black holes might retain traces of the objects they've consumed. So, what could this hair look like? One possibility is that it involves quantum fields or gravitational waves that linger around the black hole, carrying information about its past. These fields could create tiny distortions or patterns in the space-time around the black hole, acting like a kind of cosmic fingerprint. While these features would be incredibly subtle, they could provide clues about what the black hole has eaten over its lifetime. This idea has profound implications for our understanding of black holes and the universe. If black holes do have hair, it could mean that information isn't completely lost when something falls into them, a concept that ties into one of the biggest mysteries in physics, the information paradox. This paradox questions how information about matter and energy can seemingly vanish in a black hole, which contradicts the principles of quantum mechanics. The possibility of black hole hair offers a potential solution, suggesting that information might be preserved in these hidden features. Of course, this is still a highly debated topic, and scientists are working hard to find evidence to support or refute the idea. But if black holes do have hair, it would revolutionize our understanding of these mysterious objects, showing that they're far more complex and perhaps far more informative than we ever imagined. As we continue to explore the cosmos, who knows what other secrets black holes might reveal? Now, shifting our focus to another intriguing aspect of black holes, let's explore why they are often called the ultimate cosmic ghosts: because they're invisible. Yes, black holes are invisible, and not just in the way you might think. It's not that they're hiding behind a veil or cloaked in darkness. It's because their gravitational pull is so intense that not even light can escape them. Without light, there's nothing for our eyes or telescopes to detect, making black holes completely invisible in the traditional sense. But if black holes are invisible, how do we know they exist? This is where the ingenuity of science comes into play. While we can't see black holes directly, we can observe their effects on the space around them. Imagine a black hole as a cosmic vacuum cleaner, pulling in everything nearby: gas, dust, and even stars. As these materials spiral toward the black hole, they heat up and emit intense radiation, often in the form of X-rays. By detecting this radiation, scientists can infer the presence of a black hole, even if they can't see the black hole itself. Another way scientists detect black holes is by observing how they warp the fabric of space-time. According to Einstein's theory of general relativity, massive objects like black holes bend the light from stars and galaxies behind them. This phenomenon, known as gravitational lensing, creates distorted or magnified images of those background objects. By studying these distortions, astronomers can map out the location and size of a black hole, even though it remains invisible. Perhaps one of the most famous examples of this indirect detection is the first ever image of a black hole's shadow, captured in 2019 by the Event Horizon Telescope. This groundbreaking image didn't show the black hole itself, but rather the glowing ring of light around it, created by the intense gravitational forces bending the light from the surrounding material. This shadow is essentially the closest we've come to seeing a black hole, and it's a testament to how much we can learn by observing their effects rather than the objects themselves. So, while black holes may be invisible, they're far from undetectable. Through their influence on nearby matter, their gravitational lensing effects, and the radiation they generate, scientists have developed clever ways to study these enigmatic objects. And as our technology advances, who knows what other invisible secrets of the universe we might uncover. Next, we'll take a closer look at how black holes can merge, creating some of the most energetic events in the cosmos. Now, diving deeper into the cosmic dance of black holes, let's explore one of the most dramatic events in the universe: black hole mergers. Picture two massive black holes, each with a gravitational pull so strong that nothing can escape them, locked in a spiraling embrace. As they orbit each other, they lose energy in the form of gravitational waves, ripples in the fabric of space-time predicted by Einstein over a century ago. These waves travel across the universe at the speed of light, carrying with them the story of the black hole's collision. But how do we detect these gravitational waves? Enter the Laser Interferometer Gravitational Wave Observatory, or LIGO, a groundbreaking project designed to catch these faint signals. LIGO uses incredibly precise lasers to measure tiny distortions in space-time caused by passing gravitational waves. When two black holes merge, the resulting waves create a distinct chirp pattern in the data, a signature that tells scientists not only that a merger has occurred but also details about the black holes involved, like their masses and how far away they are. The first detection of gravitational waves in 2015 was a monumental moment in science. It confirmed Einstein's predictions and opened a new way to observe the universe. Since then, dozens of black hole mergers have been detected, each one revealing more about these mysterious objects. For instance, mergers have shown us that black holes can come in a wide range of sizes, from just a few times the mass of our Sun to tens of thousands of times larger. They've also provided clues about how black holes form and evolve, whether through the collapse of massive stars or the merging of smaller black holes over time. But the story doesn't end there. When two black holes merge, they create a single, even more massive black hole. The energy released during this process is staggering, often equivalent to several times the mass of the Sun being converted into gravitational waves in a fraction of a second. This makes black hole mergers some of the most energetic events in the universe, outshining entire galaxies for a brief moment. What's truly fascinating is what these mergers tell us about the nature of black holes and the universe itself. By studying the gravitational waves they produce, scientists can test Einstein's theory of general relativity in extreme conditions, probing the limits of our understanding of gravity. They also provide insights into the distribution of black holes across the cosmos and how they interact with their surroundings. As we continue to detect more mergers, we're piecing together a clearer picture of these enigmatic objects and their role in shaping the universe. Next, we'll explore another surprising aspect of black holes: their ability to generate powerful magnetic fields, and how these fields influence the cosmos around them. Now, shifting our focus to another fascinating aspect of black holes, let's explore the surprising role of magnetic fields. While we often think of black holes as purely gravitational powerhouses, they can also generate incredibly strong magnetic fields. These fields are not just a side note, they play a crucial role in shaping the behavior of matter and energy around black holes, creating some of the most dramatic phenomena in the universe. So, how do black holes produce magnetic fields? It all starts with the swirling disk of gas, dust, and other matter that often surrounds them, known as an accretion disk. As this material spirals inward, it becomes superheated and ionized, meaning its atoms lose electrons and become charged particles. These charged particles, moving at incredible speeds, generate electric currents, which in turn produce magnetic fields. The faster the material spins, the stronger these fields become, sometimes reaching intensities far beyond anything we can imagine on Earth. But how do scientists detect these magnetic fields? One of the key methods involves observing the jets of particles that shoot out from the poles of some black holes at nearly the speed of light. These jets, which can stretch for thousands of light years, are thought to be powered and shaped by the black hole's magnetic fields. By studying the structure and behavior of these jets, researchers can infer the presence and strength of the magnetic fields driving them. Instruments like radio telescopes and X-ray observatories are essential tools in this process, allowing scientists to map the jets and trace their origins back to the black hole's magnetic influence. The role of magnetic fields doesn't stop there. They also help regulate the flow of matter into the black hole itself. In some cases, magnetic fields can channel material away from the accretion disk, preventing it from falling in, and instead launching it into space as part of these powerful jets. This process not only shapes the environment around the black hole, but also influences the growth and evolution of the black hole over time. What's truly remarkable is how these magnetic fields connect black holes to the larger cosmos. The jets they produce can impact entire galaxies, heating surrounding gas, triggering star formation, or even suppressing it. In a way, black holes with magnetic fields act as cosmic engines, driving change on a scale that's hard to comprehend. As we continue to study these magnetic fields, we're uncovering more about how black holes interact with their surroundings and shape the universe. Next, we'll delve into another mind-bending concept, the possibility that black holes could serve as gateways to time travel, bending the very fabric of space-time itself. Now, let's venture into one of the most mind-bending ideas about black holes. Could they actually function as time machines? This concept might sound like science fiction, but it's rooted in the very real and extreme effects black holes have on space and time. According to Einstein's theory of general relativity, black holes warp the fabric of space-time so intensely that they could, in theory, create pathways for time travel. Imagine this: as you approach a black hole, time begins to slow down relative to someone far away from its gravitational pull. This phenomenon, known as time dilation, means that while minutes might pass for you near the black hole, years or even centuries could go by for someone observing from a distance. In essence, you could emerge from the black hole's influence to find yourself in a future that's drastically different from the one you left behind. But what about traveling backward in time? This is where things get even more speculative. Some theories suggest that certain types of black holes, particularly those that are rotating, might create closed time-like curves, paths through space-time that loop back on themselves. If such a curve existed, it could theoretically allow you to travel back to a point in your own past. However, this idea comes with enormous challenges. For one, the conditions required to create these curves are so extreme that they might be impossible to achieve in reality. Additionally, the intense gravitational forces near a black hole would likely tear apart anything or anyone attempting to navigate such a path. Even if time travel through black holes were possible, the implications would be staggering. It would challenge our understanding of cause and effect, raising questions about paradoxes like the famous grandfather paradox, where traveling back in time could create a situation where you prevent your own existence. These paradoxes highlight the deep mysteries that still surround the nature of time and whether it's truly a one-way street While the idea of black holes as time machines remains firmly in the realm of theory, it's a fascinating area of exploration that pushes the boundaries of our understanding of the universe. As we continue to study these cosmic giants, we may uncover new insights that bring us closer to answering whether time travel is more than just a dream. Next, we'll explore another striking feature of black holes, their ability to create rings of light that reveal secrets about their structure and behavior. Now, shifting our gaze to another mesmerizing feature of black holes, let's explore the phenomenon of photon rings, a stunning visual signature that reveals the intricate dance of light around these cosmic giants. When light passes close to a black hole, its path is bent by the immense gravitational pull, creating a series of rings that encircle the black hole like ripples on a cosmic pond. These rings, known as photon rings, are formed when light orbits the black hole multiple times before finally escaping, offering scientists a unique window into the black hole's structure and behavior. The formation of these rings is a direct consequence of the extreme warping of space-time near a black hole. As light travels through this distorted region, it follows curved paths, some of which loop around the black hole before breaking free. The result is a series of concentric rings, each representing light that has orbited the black hole a different number of times. The innermost ring, for instance, might consist of light that has circled the black hole once, while outer rings could represent light that has looped multiple times before escaping. These photon rings are more than just a visual spectacle. They hold valuable clues about the black hole's properties. By studying the size, shape, and brightness of these rings, scientists can infer details about the black hole's mass, spin, and even the structure of its event horizon. For example, a more massive black hole will produce larger rings, while a rapidly spinning black hole might create asymmetrical rings due to the dragging of space-time around it. One of the most groundbreaking moments in the study of photon rings came with the first ever image of a black hole, captured by the Event Horizon Telescope in 2019. This historic image revealed a bright ring of light surrounding the black hole's shadow, confirming predictions about the existence of photon rings and providing a wealth of data for further analysis. Since then, researchers have been refining their techniques to extract even more information from these rings, pushing the boundaries of our understanding of black holes. The study of photon rings also opens up exciting possibilities for testing Einstein's theory of general relativity in extreme environments. By comparing observations of these rings with theoretical predictions, scientists can look for any deviations that might hint at new physics or modifications to our current understanding of gravity. This makes photon rings not just a beautiful cosmic phenomenon, but also a powerful tool for probing the fundamental laws of the universe. As we continue to unravel the mysteries of black holes, photon rings stand as a testament to the intricate interplay between light, gravity, and space-time. They remind us that even in the darkest corners of the cosmos, there is light literally, and it holds the key to unlocking some of the universe's deepest secrets. Next, we'll delve into another intriguing concept, the idea of naked singularities, black holes without event horizons, and what their existence could mean for our understanding of physics. Now, stepping into the realm of theoretical possibilities, let's explore the idea of naked singularities, a concept that challenges our very understanding of black holes. Unlike traditional black holes, which are hidden behind the inescapable boundary of an event horizon, naked singularities are thought to exist without this cosmic veil. This means that, in theory, their infinitely dense cores could be exposed to the universe, creating a scenario where the laws of physics as we know them might break down. The idea of naked singularities arises from solutions to Einstein's equations of general relativity. While most black holes are thought to have event horizons, regions where gravity is so strong that nothing, not even light, can escape, naked singularities suggest a different reality. In these cases, the singularity, the point of infinite density at the heart of a black hole, would be visible to the outside universe. This raises profound questions about the nature of space, time, and gravity. However, the existence of naked singularities is highly controversial. Many physicists argue that nature abhors such a scenario and that some form of cosmic censorship must prevent singularities from being exposed. This principle, known as the cosmic censorship conjecture, proposes that all singularities must be hidden behind event horizons, shielding the universe from their unpredictable and potentially chaotic effects. If naked singularities were to exist, they could disrupt our understanding of causality, making it possible for events to occur without a clear cause and effect relationship. Despite the controversy, the possibility of naked singularities has sparked intense debate and research. Some theoretical models, particularly those involving rapidly spinning black holes or extreme conditions in the early universe, suggest that naked singularities could form under specific circumstances. If proven to exist, they would provide a unique laboratory for testing the limits of general relativity and exploring new physics beyond our current theories. The implications of naked singularities are staggering. They could challenge our understanding of the universe's fundamental laws, offering insights into quantum gravity and the unification of general relativity with quantum mechanics. Moreover, their existence could reshape our view of black holes, suggesting that these cosmic enigmas might not always be as hidden or as predictable as we once thought. As we continue to probe the mysteries of black holes, the question of naked singularities remains one of the most tantalizing and unresolved puzzles in modern physics. Whether they exist or not, the very idea pushes the boundaries of our knowledge, reminding us that the universe is far stranger and more complex than we can imagine. Next, we'll turn our attention to another fascinating aspect of black holes: their ability to exist in binary systems, orbiting alongside stars or even other black holes. Now, shifting our gaze to the cosmic dance of black holes, let's explore how these mysterious objects often don't exist in isolation. Black holes can have companions, forming binary systems with other stars or even other black holes. These partnerships are not just fascinating to observe, they also reveal critical insights into the behavior and evolution of black holes. Binary systems involving black holes typically form in one of two ways. The first scenario occurs when two massive stars born together in a stellar nursery evolve over time. If both stars are massive enough, they may eventually collapse into black holes, creating a black hole binary. The second scenario involves a black hole capturing a passing star or another black hole through gravitational interactions. Over time, these captured companions settle into stable orbits, creating a binary system. When black holes exist in binary systems, their interactions can be dramatic. As they orbit each other, they emit gravitational waves, ripples in space-time predicted by Einstein's theory of general relativity. These waves carry energy away from the system, causing the black holes to spiral closer together over millions or even billions of years. Eventually, they merge in a cataclysmic event, releasing an enormous burst of gravitational waves that can be detected by observatories here on Earth. One of the most exciting aspects of black hole binaries is what happens during the merger. As the two black holes draw closer, their immense gravitational forces distort space-time, creating a chaotic and energetic environment. When they finally collide, they form a single, more massive black hole. The energy released during this process is staggering, often exceeding the combined energy output of every star in the observable universe for a brief moment. But black hole binaries aren't just about mergers. In systems where a black hole is paired with a star, the interaction can be equally fascinating. The black hole's intense gravity can pull material from its companion star, forming an accretion disk around the black hole. This disk heats up and emits powerful radiation, including X-rays, making these systems some of the brightest objects in the sky. In some cases, the black hole's gravitational pull can even strip the star entirely, leaving behind a lone black hole. The study of black hole binaries has revolutionized our understanding of these cosmic objects. By observing their gravitational waves and electromagnetic emissions, scientists can measure the masses and spins of black holes, test the predictions of general relativity, and even probe the nature of space-time itself. These systems also provide clues about the formation and evolution of black holes, shedding light on their role in shaping galaxies and the universe as a whole. As we continue to uncover the secrets of black hole binaries, one thing is clear: these cosmic partnerships are more than just a curiosity. They are windows into the most extreme environments in the universe. Next, we'll delve into another groundbreaking discovery: how black holes can be detected through their shadows, offering us a glimpse into the very edge of these enigmatic objects. Now, shifting our focus to a groundbreaking achievement in astrophysics, let's explore how black holes can be detected through their shadows. In April 2019, the world witnessed an extraordinary milestone: the first ever image of a black hole's shadow. Captured by the Event Horizon Telescope, a global network of radio telescopes, this historic image revealed the silhouette of the supermassive black hole at the center of the galaxy Messier 87, located 55 million light-years away. But what exactly are we seeing in this image? The shadow of a black hole is not the black hole itself. It's the absence of light caused by the black hole's immense gravitational pull. As light from the surrounding accretion disk approaches the black hole, it bends and spirals inward, creating a dark region at the center. This dark region, surrounded by a glowing ring of light, is what we call the black hole's shadow. It's essentially a visual representation of the event horizon, the point of no return where nothing, not even light, can escape. The process of capturing this image was no small feat. The Event Horizon Telescope combined data from multiple telescopes across the globe, effectively creating a virtual telescope the size of Earth. This allowed scientists to achieve the resolution needed to observe the black hole's shadow despite its immense distance. The data collected was so vast that it had to be physically transported on hard drives to be processed, a task that took years of meticulous work. So, why is this shadow so important? For one, it provides direct visual evidence of black holes, confirming predictions made by Einstein's theory of general relativity. The size and shape of the shadow also offer clues about the black hole's mass and spin, helping scientists refine their understanding of these enigmatic objects. Additionally, studying the shadow allows researchers to test the limits of our current theories about gravity and space-time, potentially uncovering new physics. The image of the black hole's shadow has opened a new window into the study of black holes, offering a tangible way to observe and analyze these cosmic giants. It's a testament to human ingenuity and collaboration, showcasing how cutting-edge technology and international cooperation can push the boundaries of our knowledge. As we continue to refine our techniques and capture more detailed images, the shadows of black holes will undoubtedly reveal even more secrets about the universe's most mysterious objects. Next, we'll delve into another intriguing aspect of black holes: the controversial idea that they might have firewalls at their event horizons, challenging our understanding of these cosmic phenomena. Now, turning to one of the most debated ideas in modern physics, let's explore the controversial firewall hypothesis. This theory challenges our traditional understanding of black holes by suggesting that the event horizon, the boundary beyond which nothing can escape, might not be as smooth and uneventful as we once thought. Instead, it could be a blazing wall of intense energy capable of incinerating anything that crosses it. The concept of a firewall at the event horizon emerged as a potential solution to a paradox in quantum mechanics known as the black hole information paradox. According to quantum theory, information about matter and energy cannot be destroyed. However, if an object falls into a black hole, it seems to vanish completely, leaving no trace of its existence. This contradiction has puzzled scientists for decades. The firewall hypothesis proposes that the event horizon acts as a destructive barrier, burning up anything that enters and preserving information in the process. But this idea comes with its own set of challenges. For one, the existence of a firewall would violate Einstein's theory of general relativity, which predicts that an object crossing the event horizon should experience nothing unusual, a principle known as the no-drama scenario. If firewalls are real, it would mean that our understanding of gravity and space-time is incomplete, requiring a radical rethink of how black holes operate. This has sparked heated debates among physicists, with some arguing that firewalls are a necessary consequence of quantum mechanics, while others believe they are a sign that we're missing a crucial piece of the puzzle. The implications of the firewall hypothesis are profound. If proven true, it could revolutionize our understanding of black holes, quantum mechanics, and the very fabric of the universe. It might also provide new insights into the nature of information and how it interacts with gravity. However, the idea remains highly speculative, and scientists are still searching for ways to test it experimentally. Some propose that studying the behavior of particles near the event horizon or analyzing gravitational waves from black hole mergers could offer clues. As we continue to probe the mysteries of black holes, the firewall hypothesis serves as a reminder of how much we still have to learn. It challenges us to question our assumptions and pushes the boundaries of our knowledge, highlighting the intricate dance between quantum mechanics and gravity. Whether firewalls exist or not, the debate itself is driving progress, bringing us closer to unraveling the secrets of these cosmic enigmas. Next, we'll examine how black holes provide a unique testing ground for Einstein's theory of general relativity, offering insights that could reshape our understanding of the universe. Now, shifting our focus to one of the most groundbreaking applications of black holes, let's explore how these cosmic giants serve as a unique testing ground for Einstein's theory of general relativity. For over a century, Einstein's theory has been the cornerstone of our understanding of gravity, space, and time. But black holes, with their extreme gravitational fields, offer a natural laboratory to put this theory to the ultimate test. General relativity predicts that massive objects like black holes warp the fabric of space-time, creating effects such as gravitational lensing, time dilation, and the bending of light. These predictions have been confirmed time and again, but black holes push the theory to its limits. Their immense gravity creates conditions so extreme that they challenge our understanding of physics itself. For instance, the recent detection of gravitational waves from black hole mergers has provided some of the strongest evidence yet for general relativity. These ripples in space-time, first observed in 2015, match Einstein's predictions with astonishing precision, confirming that black holes behave exactly as the theory suggests. But not all observations have been so straightforward. Some phenomena near black holes, such as the behavior of matter in their accretion disks or the mysterious properties of their event horizons, have raised questions that general relativity alone cannot fully explain. For example, the way light behaves around black holes sometimes hints at deviations from Einstein's predictions, suggesting that there might be more to gravity than we currently understand. These anomalies have sparked interest in alternative theories, such as modified gravity or quantum gravity, which aim to bridge the gap between general relativity and quantum mechanics. One of the most exciting developments in this field is the Event Horizon Telescope's image of a black hole's shadow, captured in 2019. This historic image not only provided a visual confirmation of black holes, but also allowed scientists to test general relativity in the strong gravity regime near the event horizon. The results aligned closely with Einstein's predictions, but they also opened the door to further exploration. By studying the subtle details of these images, researchers hope to uncover clues about the nature of gravity and whether general relativity holds up under the most extreme conditions. Black holes continue to be at the forefront of scientific discovery, offering a unique window into the fundamental laws of the universe. They challenge us to refine our theories, question our assumptions, and explore the unknown. As we gather more data from gravitational wave detectors, space telescopes, and advanced simulations, we inch closer to understanding whether general relativity is the final word on gravity, or if there's a deeper layer waiting to be uncovered. Next, we'll delve into the ultimate fate of black holes, exploring theories about their longevity and whether these cosmic titans might one day vanish from the universe. Now, turning to the ultimate fate of black holes, we find ourselves confronting one of the most intriguing mysteries in astrophysics: the possibility that black holes might not be eternal. For centuries, these cosmic giants have been seen as indestructible, their immense gravity trapping everything that crosses their event horizon. But modern science suggests that even black holes may have an expiration date. The key to this idea lies in a phenomenon known as Hawking radiation, proposed by physicist Stephen Hawking in the 1970s. According to this theory, black holes are not entirely black. Instead, they emit tiny amounts of radiation due to quantum effects near their event horizons. Over unimaginably long timescales, this radiation causes black holes to lose mass, slowly shrinking until they eventually evaporate completely. For a typical stellar mass black hole, this process could take trillions upon trillions of years, far longer than the current age of the universe. But for smaller black holes, the process could happen much faster, potentially leading to their complete disappearance. However, the story doesn't end there. Some theories suggest that black holes might not simply vanish but could instead transform into something entirely new. One speculative idea is that as a black hole evaporates, it leaves behind a remnant, a tiny, ultra-dense object that contains the information about everything it once consumed. This remnant could be a bridge to new physics, offering clues about the nature of space, time, and quantum mechanics. Another possibility is that black holes could give birth to new universes, with their collapse triggering the creation of an entirely new cosmic reality. While these ideas remain highly theoretical, they challenge our understanding of black holes as eternal prisons and open the door to fascinating possibilities about their ultimate fate. The implications of black hole decay are profound. If black holes can evaporate, it means that even the most powerful objects in the universe are subject to change and transformation. This challenges the notion of permanence in the cosmos and raises questions about the long-term future of the universe itself. Could the eventual evaporation of all black holes lead to a universe devoid of these mysterious objects? Or might their remnants play a role in shaping the cosmos in ways we can't yet imagine? As we continue to study black holes, we are reminded that even the most seemingly eternal aspects of the universe are part of a dynamic, ever-changing tapestry. The ultimate fate of black holes remains one of the great unsolved questions in science, inviting us to explore the boundaries of our knowledge and imagine the possibilities that lie beyond. With each discovery, we come closer to understanding whether black holes are truly eternal, or if they, like everything else in the universe, are destined to transform. As we bring our journey through the mysteries of black holes to a close, it's clear that these cosmic enigmas are far more complex and fascinating than we once imagined. From their ability to spin at nearly the speed of light to the mind-bending possibility that they might not be eternal, black holes continue to challenge our understanding of the universe. We've explored how they can stretch objects into spaghetti-like strands, power some of the brightest objects in the cosmos, and even produce sound waves that ripple through space-time. Yet, with every discovery, new questions arise, reminding us just how much we still have to learn. The 20 unknowns we've uncovered today are just the tip of the iceberg. Black holes remain one of the greatest frontiers in science, offering endless opportunities for exploration and discovery. Whether it's the mystery of their ultimate fate, the potential for them to create new universes, or the tantalizing hints they provide about the nature of space and time. These cosmic giants hold the keys to unlocking some of the universe's deepest secrets. So, what do you think lies beyond the event horizon? Could black holes truly be gateways to other dimensions, or are they simply the ultimate cosmic recyclers? The answers may still be out of reach, but the journey to uncover them is as thrilling as it is enlightening. If you've enjoyed this deep dive into the unknown, don't forget to share your thoughts in the comments below. What aspect of black holes fascinates you the most? And if you're hungry for more cosmic mysteries, be sure to hit that subscribe button and ring the notification bell so you never miss an update. The universe is full of wonders, and together we'll keep exploring them one black hole at a time.